Streaming. Okay, hopefully this works. There's a little bit of a delay, so we'll see how it works.
Yeah.
Welcome everybody to Starry Nights at Simon Fraser University. My name is Kyle, and joining with me is...
Hi, everyone. My name is Abby.
All good. All right, so
Yeah.
Abby and I will be your hosts for tonight. And joining us in the chat is longtime staff members Rohit and Zena, along with Rob from the Royal Astronomical Society of Canada, or RASC, as we like to call ourselves. They'll be joining us in the chat to answer any questions, and we'll launch from there. Just as a little word of warning, because... Actually, I'll say this first. Can everyone hear me? Can everyone hear us? Abby and I.
Yeah. Just we want to check, see if our audio is going through before we start.
Yeah, exactly.
Yeah.
Just make sure. And yeah, there's still a little delay. So we'll see how this goes. Oh, okay. Zena says she can hear us. Okay. Well, and more people are coming in. Okay, perfect. So we are good and ready to go. So, a little bit of forewarning. As you can see in that bottommost camera, there's a little bit of unexpected clouds that just came in, like literally half an hour ago. So we're going to try our best to look at some really cool things. But we're going to see how this goes. It might go a little bit shorter, but we'll see how it goes. Yeah, I don't know if you want to add anything, Abby.
Yeah, it's a little bit unexpected because throughout the week, SFU, we're on the mountain. It's been really nice up here because, I know the lower mainland has been covered by fog, but as we're like the floating island and the floating island and the mountain, it's been so clear. So it's a little bit unexpected. But yeah, hopefully everything will be fine. Well, if everyone's in the chat, how is your fog experience here in Vancouver?
Oh my god.
How's it in your area? Yeah, I heard it's so bad.
Like
in some area.
Oh my gosh, like over the past few days, like when I was driving, just like, I don't know, up to the school or just over into New Est, it was so thick. It was so scary. I couldn't even see the streetlights until it was like, I don't know, 100 meters away or something. Like it was dense, and I was scared.
It was. Okay. Yeah, so right now you'll be looking at a nebula, but we're trying to recenter our telescope, so this take a while, but yeah.
All right, here, let me give it a little go here. So let me just move it ever so slightly. And we're going to go over here, and then...
Yeah. So we have to click to find recenter in the nebula in here.
Whoa!
Oops, yeah, we get something. So yeah, the telescope is still moving while we're taking a long exposure. So that's like all the trails you could see on the screen. Yep, now it's fine.
Oh.
Yeah, so so a lot of times taking astrophotography, it's about long exposure because these objects are really, really faint and they're harder to pick up by just naked eye. And even though we're using some equipments, it will take really long time to take a nice picture.
Mm-hmm. Oh, exactly.
So right now you can see I am adjusting the color levels in here, trying to align them to make a more balanced picture.
I think that looks pretty good.
Yeah, that's really nice. It's a little bit greenish though. I'm trying to tune down the green level.
Mm-hmm. Okay. I'll just say a little bit of something about this while you're kind of doing that. So yeah, what Abby just said is when we're taking long exposures of distant objects, like if you're searching up this, for example, this is the Orion Nebula. But let's say, for example, you look up some object in space on Google, and they have these beautiful, majestic mosaics of an image, right? And that's the result of well, maybe not hundreds, but lots and lots of hours of exposing the camera to that particular object to let all the light in all at once, or sorry, over time rather, and then compile that into an image. Unfortunately, our eyes don't actually or can't do that. Because as soon as a photon hits our eye, it immediately just gets transferred into data that is sent to our brain, which is cool in and of itself. But we're doing astronomy here, not biology. But anyway, but the reason why we can see the Orion Nebula this well is because the object itself is actually pretty bright on its own. It is, I think, the only naked eye nebula. Like, you can see this; it's right below Orion's belt, and on a nice, even a semi-ish dark night, like even in the city, you can just barely see it. But you can see it with your naked eye. But if you go out into out in the middle of nowhere, like a really good place I like to go is the Cascade Lookout in Manning Park. Super, super dark. You're away from all sorts of lights. And, for example, this nebula is spectacular to the naked eye as well. But even now you can see that right in the center, there's like a little kind of cluster of stars there. And that's a cluster of 4 stars called the trapezium. So I want to say that. Yeah, and just those 4 stars provide all the illumination for the entire nebula. It is fantastic. Yeah. I don't know if you want to talk about anything else, Abby, but
yeah, just like adding on to your point, like it's so great when you can see a messy object with naked eye. I was like, remember one summer I was in Yellowknife. Well, sadly it's summer, so you can't see a winter object. But if you wait till later in the evening, you're able to see something like from the winter, and like in the middle of the night. I saw the Pleiades with my naked eye. I was so happy. It was like a really great experience. Yeah, the only sad thing is that it was a full moon night, so that's why I couldn't see much thing with nebulosity, but star clusters are fine.
Star clusters are pretty easy to find. I mean, they're just a big bright cluster of stars. The really cool stuff, the nebula, those are tricky.
Yeah, they are.
One thing I noticed, though, is that it looks like this nebula is like, there's lots of red, there's some orange there. What's up with that? Like, why is it red?
Yeah, so when you can see red, it indicates it's hydrogen, isn't it? Yeah, that's I remember. I could be wrong here, but I remember. Yeah, that's what I remember.
I think that's right.
Red color. It's usually there are a lot of hydrogen inside.
And that's all that hydrogen. So it's the radiation from the trapezium, actually, in this case, that's ionizing the gases around it, creating those brilliant red colors. We'll try, emphasis on try, later tonight. I mean, we can try the Crab Nebula and see what happens, but that's a nebula that might be in a different color, because it is technically a supernova remnant. But we'll see about that later tonight. I guess some really cool things about the nebula itself is it's 1,300 light years away. So we're seeing it as it was over 1,000 years ago. What else can and how wide it is it's 24 light years in diameter. This is a massive object in the sky. Oh.
Yeah, I wonder how it looked like if it's today, or if we're looking at today in the actual one. It's really fun or interesting that astronomy, it's like time travel. Whenever you look at an object, you're looking into the past and how they look like in the past. Yes. Since like everything gets so far away.
And it's amazing. Like, one really cool thought experiment that I keep thinking of is like say, for example, we're on a planet that's in another galaxy and it's 64 million light years away, for example, and we had a super powerful telescope and turned it towards the Earth, we would be seeing dinosaurs walking across the surface. That's how, like, when you're looking back in time, that's what's happening. Like, light takes time for it to get to places, right? And the universe is just so big. So I think that's, yeah, it's really cool to think about that kind of stuff. And what was I going to say? Oh, yeah, and the thing with the James Webb telescope, now that's a whole new thing we can talk about. Whole other thing, rather, we can talk about. But yeah, the James Webb telescope that reached Lagrange point 2 is supposed to peer ever so slightly further back into the universe than our current telescopes can. So this will be really, really cool to see what comes of that.
I can't wait for the first image to come.
Oh my god, me too. And
yeah,
and it's mostly, I think it's mostly like an infrared telescope, right? Is it infrared or ultraviolet?
I don't remember that,
yeah.
But I think it could be both.
Well, it could be both, yeah. Someone in the chat can help us out when we're going through. What else can we say?
Yeah.
Let's see. Yeah, so this is also, I think, Xena got it with the ionized, super creative with the trapezium. Yeah, the other thing is that this is what's called a stellar nebula. So that means this wasn't formed by any, like, supernovas, because those are called supernova remnants. But this is a stellar nebula. So this is just a nebula that just has existed in space and is slowly collecting into, or slowly pooling together to make stars. But there are probably about, so this is an active area of star formation, right? And I think there's around 700 stars in various stages of formation that's in the nebula right now, which is really, really cool.
Yeah, I love the Orion Nebula a lot. It's super bright.
Super bright. It looks so cool. It's one of my favorite objects to see when it's dark. Oh. Okay. So that's the Orion Nebula. Maybe let's try another bright object. Is there what kind of, do we have a star cluster that maybe we can try out?
Yeah, we do. We could try M3. It's a globular cluster.
Okay, let's do it.
Yeah, let's do that. So, yeah, I can go. Do you want to do that, Kyle? Or do you want me to do it? I can do it.
Go for it.
Yeah, I can go.
Bip, 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 bip. Bip, bip, bip. Looking at space. I don't know. I was super pumped. I was like, I didn't live stream the James Webb Space Telescope, like the launch of it, but I was on there. Like, NASA came out with a really good website called Where is Webb, and it had all this information of like where the telescope was, what stage it was in its unfolding process period, and also what temperature the telescope is at as well. And I was following that every day. At one point, it was traveling 1 mile per second, 1 mile per second, which is incredibly fast. But what really floors me every time is the temperature on the telescope itself, because it has a big sunshade, right? On the sun-facing side of the telescope, it is probably about 100 degrees Celsius, right? Which is wicked. But then also on the other side, because it's in the shadow, the temperature drops to like minus 200 degrees Celsius or something around there. Like, the temperature difference really just boggles me every time. Um,
Okay, Cal. So
yeah.
turns out some of those clusters are still below the horizon. So
Oh,
I'm trying another nebula now.
okay, sure, go for it. Which one?
I'm trying the Lion Nebula.
The Lion Nebula. Okay, let's do it. Is
Oh,
that it right
I
at
can
the
see.
bottom there?
Um, yeah, the nebula is here, but it seems like some of the frames are ignoring. So I'm trying to see what the issue is. Yeah, because we got a really good image last night.
Mm-hmm.
It could be, yeah, because of the clouds, or it could be
I think
it's
that's
still
yeah.
slightly bright out there. We might be looking at through the thin clouds.
Right. Let's have a look. So where's the telescope? So the telescope's pointed just to the east there slightly. So I think there might be some thick-ish cloud cover over there. But just for the purposes of discussion, so that is the nebula right in the. Oh.
Okay, I'm trying something in here, so I can try bin 2.
Okay.
And yep.
Yeah. So that blue patch at the bottom there, that was the nebula. Once we get it back. So because it's a little bit dimmer, what we're trying to do is we're going to turn up the exposure time to allow more light in. And already I can see it's looking pretty darn good, actually. Yeah, it's that hazy blue white thing at the bottom there, right above the logo. Oh.
Yeah, it's right here. I think we're picking up a lot of noises from some source, as I can see from the graph in here.
Hmm.
Yeah, but yeah, it's there. It's pretty. This blue little bulb, it's the nebula we're looking at.
Oh. What can you tell me about it? Because this is one I don't quite know a lot about.
Well, I know it's also limited. We're all here learning. So we're looking at the Lion Nebula. Yeah, so the Lion Nebula, it's 5,000 light years away in Gemini. So a light year in astronomy, it's the distance traveled by light in a year. Like, this is the fastest thing in the world. So imagine what if, yeah, the distance traveled by light in a year. It's a really, really long distance. So 5,000 light year means that it's a really, really long distance. Right, Cal? I couldn't imagine that. It's so hard to imagine such thing.
Oh my gosh, exactly. Like, so 1 light year is, I think, somewhere around 9 trillion kilometers, and that's trillion with a T, ladies and gentlemen. Like, that is an incredibly far away. So when we're on scales like this, and scientists, mathematicians, we're lazy. We don't want to write a number with 9, 12, 15 zeros in it. So we shorten it down to light years. So 1 light year is 9 trillion kilometers. So this is 5,000 of those away. And again, we're seeing it as it was about 5,000 years ago. It's incredible. And this is a planetary nebula, right?
Yes, this is a planetary nebula.
What makes a planetary nebula?
A planetary.
I can take over if you want to.
Okay, yeah, sure, you can take over. Yeah, so a planetary nebula, it's not a planet. It has the name planet in it, but it doesn't really say it's a planet. So imagine like a star, like our sun. Stars also have their own lifetime. So when the star gets older, it blows up itself. It gets bigger and bigger. and at some point it will explode. That's kind of like, yeah, when it explodes, and yeah, sorry, when a star like the mass of our sun explode, it becomes a planetary nebula because it's blowing its own material towards the space. So that's why you can see there's a layer, there's like a blob surrounding the dying star. So the white dot in the middle is like a dying star you can see. Yeah, and like Cal said, later on, we'll be looking at a different type of nebula. So that would be a different, yeah, that's a different type of star corps that we'll see in the and later in the webinar. So basically, yeah, you're looking at a Death Star when we're looking at planetary nebula.
Oopsie doopsie. Ah, that's too much blue.
Yeah.
All right, come on. Don't fight with me. There we go. Okay. So yeah, I can see the quality kind of the image has kind of degraded a little bit over time, and that might be due to the clouds that are coming in. It's starting to glare and take away from the image. So,
yeah, because we're looking into south-ish now, I believe.
Right.
Or we're looking into, yeah, there are quite a lot of clouds in that direction.
Okay, fair enough. Okay, then maybe, okay, so that nebula is probably a little dimmer. Maybe let's try, let's see, what's a good, I'm trying to think of a star cluster again. What's another good star cluster? Okay, I'm going to try, let's try the Pleiades. Now, the thing is, with the Pleiades, is that the Pleiades is, it's the closest star cluster to Earth. Now, with it being that close, it might actually, we might only discern maybe like 1 or 2 stars in the image. Let me just zoom out again, just so we have an idea. Okay. So, there's our little zoomy. Now, another name for the Pleiades are called the Seven Sisters. And the reason for that is on a clear, dark night, and if you have... I don't have good eyesight, so I wear glasses. But if you have really good eyes, there are 7 really bright stars in this cluster. They're bright blue stars, and you know what? And I think it is too big.
Yeah.
Ian.
Let's try to focus on one star.
Yeah. So let me just zoom in. I'm just gonna zoom in, so we're right in the middle there. Let's maybe go over something like there. Go boink. Let's slew over there. Okay. Boink. And what's really tricky to see for the Pleiades is actually there's some photos of the Pleiades that have some like blue-ish nebula around it, very faint and very diffuse. Bluish nebula. Okay, there's part of it. Just going to refresh and let it stack again. Really good astrophotographers, they're able to capture this very slight diffuse gas that's around the Pleiades. And I'm not sure if this is actually a nebula that surrounds the Pleiades itself, or surrounds the Pleiades itself, or it's in front of it, or behind it. But it's really cool to see that kind of blue nebulosity.
Yeah, I think it makes the star cluster more interesting and make it more pretty, because you can see quite few, or maybe some other star clusters, you tend to see less nebulosity in it, but this you see a lot of it.
Come on. Oh, dang.
Oh,
Oh, that means I went the other way. Oops, I want to go this way. All right, we'll go like that. Whoop. I'm not coming in. Oh, there's one.
Yep. Oh, it's so pretty. We got it.
Wow. So that's a really crisp blue. I think that's, yeah, so I think these stars are kind of they're bigger, bluer stars. Moderators in the chat, if you can correct me if I'm wrong, but I think the Pleiades are kind of the, not blue giants, but they're kind of bigger, bluer stars than some, than yellow stars.
Yeah, I think you're right. I remember Pleiades is mostly with type A and type B stars. So.
Oh, okay. So type A, type B. So I'm thinking of, there's something called the HR diagram, which describes the luminosity of stars and the spectral type of stars, as well as the temperature. And it's, see, how I remember it is from, there's a professor, Howard Trottier, who taught up at SFU, and I remember the abbreviation for how to remember the spectral type was, oh boy, an F grade kills me. So I think these stars are O and B. I think that's what these... So you were saying type A and B. Does that mean type O and B?
It's type B and type A. So there are blue stars.
Oh, they are... Okay, so they're not quite as hot, but okay. Okay, yeah, just looking in the chat, yeah.
Yep, that's correct.
Type B. Okay, cool. All right. Yeah, so now back to the point. So the cluster itself is pretty diffuse. It's a fairly young cluster, and an indication for this is because of the type of the stars. They're blue stars, so they're, blue is very, very hot. So that means the star burns brightly, but burns through its fuel quickly. And because the cluster is so spread apart, it hasn't had enough time to, cluster together even more and make a more densely packed star cluster. Let me just consult my brain, which conveniently looks like a spreadsheet here. That this is, yeah, so it's a fairly young star, probably, probably a few, 100 million years about, just looking in the chat. So it's a few million-year-old star cluster, which is pretty young in terms of astronomy timescales. And there's probably about 50 or 60 stars in the cluster itself. But it's so close to Earth that you can see it with the naked eye. And how you can get there is, I am quickly going to, if you can identify the Orion constellation. In fact, what might help is...
Yeah, we can show them the...
Yeah, if I put this up on screen, I'm just going to do... I'm just going to hover this over to see if I can get it centered there in the stream. Whoops. I made it big. Not quite. Oops.
Yeah, I think it's on stream.
Okay, anyway, point is, if you find Orion, see, and this is the limitations with technology. If we were in person, this would be Really, really great. But if you locate Orion, there should be a very bright star, kind of. So you have Betelgeuse as the right shoulder, which is kind of an orangish star, and then you have the bluish, whitish star on his left shoulder. Then there's another bright star, if you hop over, called Aldebaran, that is in the constellation Taurus. And if you keep following that line, you'll eventually reach a kind of a fuzzy-itch patch in the sky. And that is the Pleiades star cluster. Which is really big.
Oh, where did that? We're fine. Yeah, so looking at Pleiades, like in a lot of image, you might see a very specific star or splitting the stars, but it's harder to do that through human eye, through naked eyes. So if you wanted to see specific stars from Pleiades, you'll need to split it with a binoculars or a telescope.
Okay, found 5 there, so that's all good. Let's see. Okay, so we can still see star clusters pretty good. And then let me just check let's check the cameras here. Clouds are looking okay. I guess we can still see the star cluster pretty good. Maybe let's try another nebula.
Sure.
So we've got.
We can try the Crab Nebula.
Oh, yes.
Now that we're in Taurus, so let's do that.
Yeah, now that we're here in Taurus, good idea. So let's try Crab Nebula. See where we go. Crab. Clear that. Now, again, the Crab Nebula, like I said earlier, is a supernova remnant. And so what that essentially means is it is the corpse or the guts of a long dead star that was once there.
Or maybe like someone in the chat had mentioned that it's like the graveyard of stars.
Oh, that too, yeah. And a graveyard.
Another good analogy.
Okay, just waiting for the exposure. A little tricky to see.
Yeah, so we're now looking into a supernova remnant. So unlike the planetary nebula we saw earlier, which is formed by a sun-like star, for these stars, they're much bigger and more massive to begin with. So that's why they can gain more mass. So when they get older, they'll turn into a star called the red supergiant, and it's a really, really huge star. I think Betelgeuse is also one of the red supergiant, and yeah. So when they die, they will explode themselves into like a cluster of nebula, and a lot of gaseous object in there. Yeah.
I'm having a little trouble finding it here.
Okay. See.
Yeah, this one's always tricky because this one is a pretty dim one at the to begin with, and mixed with the clouds.
Yeah. Let's try with bin 4. Bin 4 gives like brighter object.
And hold on, run that by. So what does binning mean again? So bin 4, what does that mean?
So a bin 4 means that you're combining a 4x4 pixel into one pixel. So a 4x4 would be 16 pixel into one pixel called a superpixel.
Oh, so it takes the light from 4 pixels and combines it into one?
Yeah, so that's how you can give a brighter image, because there are some brighter pixels that balances out the other.
Oh, interesting. Okay.
Yeah. Also, it's a way, if you're into astrophotography, some people, they use binning because it saves their memory space.
Okay.
So yeah, it's in the bottom of the frame, but yeah,
so
okay.
Whoops.
Oops, okay, reset it. Yeah. So let's okay, let me just clear it again and see. Yeah, hopefully it worked this time. Yeah, so for binning, most people, they focus on luminance frame, because luminance frame, there are the pictures that picked up the structure of the celestial objects you're taking in, and the RGB frame are just adding colors. So some people think RGB, it's important, but it's less important than luminance because it's only giving the color pixel. So it doesn't really it doesn't really matter for the structure. So some people, they use a higher binning for color to save space.
Okay. Interesting.
Yeah, that's also what we're doing in our observatory occasionally when we're doing astrophotography. We use a lower binning for luminance, so we can get a higher resolution and more clear structure of the celestial object, and we use a higher binning for color just to get the color pixel.
Okay. Interesting. Just peering over the chat with the chat here, and yeah, it looks like
Yeah. Okay.
Crab Nebula went supernova about 1,000 years ago. Yeah, exactly. Good point. So this nebula was actually seen by humans in in the year 1054. 1054 CE, and I think for when I was checking the sources, I think it was mostly documented in Chinese scripture. So the Chinese astronomers saw it, and they documented it. And this supernova was a new star, quote unquote, that illuminated the night sky for 2 years, I think. I think it was about as bright as the maybe not the full moon, but pretty close, for 2 years. And it was a new star before it slowly faded away. But I thought this was really cool. So pretty much the nebula, if I can just grab the mouse really quick. So the nebula should be at the very bottom, kind of in this area here, just in the very bottom. It's
where my cursor is pointing towards, circling around. Yeah, so that's the Crab Nebula we're looking at. So it's a really faint object, so it's much harder to pick up the light from it.
Yeah, and there's fantastic filaments, but I think with the clouds that it's really, really thin clouds, so it's a little trickier to see here. Not as much detail. Anyway. What am I talking about here? Crab Nebula. But yeah, so the Crab Nebula wasn't big enough to... Oh yeah, that's the other thing. So it's the result of a supernova. And what was left over is the core of the star that started to contract. And just like a figure skater pulling in their arms, they start to spin faster and faster and faster. So that's exactly what's happening with the star that made the nebula. Is the star started to contract and it started to spin faster and faster and faster until we get something called a pulsar. A pulsar. So it's a rapidly spinning star, and it spins at about a rate of 30 times per second, which is incredibly. And how we know that is because pulsars, they actually emit two beams of energy from both the poles, north and south poles, and those beams line up with Earth pretty much like a lighthouse. So we see a brightening. And we measure that, and we measure a rate of 30 times per second in terms of the spin. And luckily, it stopped there. But in other cases, some supernovas, what's left over is the stars keep going. So they keep contracting farther and farther. And now that is due to the initial mass of the star. If it's a higher mass, then it'll contract further. But you could get something called neutron stars, which are so compact that the atoms themselves, the electrons and the protons, have contracted and have combined to form neutrons. So you literally have a ball of neutrons. Like the star is just made out of pure neutron. And one step further is becoming a black hole, which are just amazing, amazing pieces of, or just amazing things in the sky. Because they don't follow physics, they don't follow the rules, so they do their own thing.
Yeah, the night sky is so interesting.
Oh gosh, it's so fascinating. Okay, anyway. Maybe let's try, what else can we look? Can we try the cat's eye? Is that worth it?
Yeah, let's try it.
Okay,
yeah,
sure.
let's check if it's. Yep, totally. Okay, I'm gonna try to look. Okay, this cluster is a little bit too low. Okay, so we can try the cat's eye.
Okay.
Okay.
Oh, that's fine.
Yep. Yeah, it's high enough.
Okay. So we're being ambitious with looking at these objects. Because normally it's great to see these objects, of course, when there's no clouds in the sky. But we're being a little ambitious with looking at those tricky objects here. But it's worth it. It's worth it if we do see it.
Totally.
And the cat's eye is another planetary nebula. And we can't get anywhere near the quality like you see in on Google in the internet. But I think we can get it to pretty decent detail. We can bring it up here.
Yes. So let's go try clear it.
Oh yeah, other fun fact is our sun will eventually become a planetary nebula, just like the cat's eye that we're going to be looking at pretty soon. Our sun isn't big enough to form a pulsar or go supernova like we just saw with the Crab Nebula, but it is big enough to, when it does eventually die, will shed its outer layers, and what's left over is something called a white dwarf, which is just, it's the leftover material that wasn't hot enough to fuse. So in the case of our sun isn't hot enough to fuse carbon together, because carbon is just too big of a molecule, or too big of an atom for our sun. But what will be left over is just the core of carbon, essentially. It won't be fusing, so it's not technically a star. But what will happen is our white dwarf sun will cool and cool and cool down over trillions of years. Now, it's hard to cool an object in space, is because there's no atmosphere to radiate heat away. But there is some, and it'll eventually cool down. But the process takes trillions of years. And this is what happens to white dwarfs over time, is that they eventually cool down into something called black dwarfs, which they're not black holes, they're just really, really cold cores of leftover stars. And it takes so long to reach this process, or to reach this stage, the process I should say, that we think there are no black dwarfs in the universe right now. Is because it takes so long to reach that point. Is that it? Just at the bottom of the screen there?
Yeah, I think it is. I'm trying to check if I'm on the right position.
Sure.
Though.
It's a little bright in the... I mean, the whole nebula itself is small. Well, okay. Small as in far away. But it's decently bright for something that's far away. So that's why it kind of looks like a star at this point. I think that's it right there.
Yes, that it is.
Just looking at the chat right now. So yeah, Xena. So yeah, brown dwarfs are, because that was a comment about brown dwarfs. Brown dwarfs are, they're really, really hot. I guess they're stars. They're not fusing anything, but they're bigger than gas giants. So they're still really, really hot. They're also called failed stars. So they're objects that didn't quite get hot enough to fuse and become a star, but they're just too big to be considered a planet. So, yeah, just having a look here. Oh yeah.
Okay, yep, I got it.
If you keep going down.
Yeah. Okay, I'm looking at the stream, so it seems like part of it's cropped out of the stream, so I'm trying to get it back.
All good.
Yeah.
Here, maybe, let me have a go. Maybe I can try and get it here.
Yep, okay, yeah, we can see it. So it's this like a little blue pink bulge thing in here.
I'm just gonna test something.
No, it's doing good now.
Oh, it's...
So...
Just... Oops. A little too far. Uh-oh. There it is. That's pretty good. Okay. Okay. So there's the nebula there, and I accidentally took out the thing there, but it should be okay. Okay, so there's the nebula there. I just want to try if I can just dim this down. Maybe a little bit of structure might pop out. Oops, no, too far. Yeah, it's still a little bit blurry, but think that's okay there.
Yeah. But it's so pretty. You can see it's really round circular shape, and the brighter
Yeah.
dot in the middle is a dead star.
Yeah, like a little oval shape, right?
Yeah,
That's
it
kind of neat.
is. It looks like one.
Huh. And then the bright stars. Bright spot. Exactly. Cool. Cool. What do you say about cat's eye? This is another one. So yeah, this one's about 3,000 light years away from Earth. Now it's around. It's difficult to determine its luminosity, and I think that's because it's kind of a brightish object on its own. It's a brightish object, and just at face value, there's not a lot of structure, and it's also really, really small. So it's hard. It's a little tricky to determine distance from that.
Yeah, because one of the important things to determine distance is that we have to know the luminosity. Yeah, I remember about some astronomical distance, about measuring different items. You use different methods. So for stars, since they're relatively closer to us, we usually use the method called the parallax. And for nebula, they're a little bit further away, so we have to determine the distance based on the luminosity and based on some equation.
Fancy physics and math.
Yeah, fancy physics stuff. I remember for distance of nebula or galaxies, you need to use like flux, also luminosity, and some sort of fancy thing, super fancy thing.
I was gonna say, oh yeah, one cool thing about the parallax method is it's really clever. Just by thinking about it. There's just here. I see what you're doing here. If I can take over the mouse.
I'm trying to put it back to.
I think there's a little box right there.
Oh, yep, you did it. Yeah.
Okay. What was I saying? Yeah. So the parallax method, it's really kind of clever. So, and you guys can do it right now too, is if you stick out your thumb about arm's length away, close one eye, and kind of focus on something in the background, and then quickly close the other eye and open the one you just closed. So kind of alternate between opening and closing each eye. And you'll see that your thumb looks to be in two different places. But the thing in the background more or less stays the same. That is parallax. And it's also the same phenomenon if you're driving down the highway. Things that are closer to you, like trees on the side of the road, will pass by you faster than, say, the mountains or buildings in the far, far background. So we can use that to our advantage by measuring the distance to nearby stars, where the Earth is on one end of the sun, and we take a photo, and then of a particular star we want to know. We take a photo, and then we wait until the Earth orbits the sun halfway, and then we take a picture of the same star on the other side, and we compare the two. And we see that the star has almost moved with respect to the background stars. It appears to move, I should say. And from that, we also use, fancy math and physics that will tell us the distance to that star. And just like what Abby said, where unfortunately there's a limit to this process. This is only for nearby stars. When we're looking at more distant stars that we want to take a picture of or be interested in, we have to use a different method. And that method is luminosity, or how bright something is. But we can't use parallax anymore because that's kind of like going back to driving down a road. analogy. That's where if you're driving down the road and you want to know how far away a mountain is with respect to a much further away mountain, it gets a little tricky. The mountains aren't really moving with respect to you driving down the highway as much as, say, a tree would just on the other side, just on the side of the road. So that's kind of where this method kind of falls apart, is for more distant objects.
Yeah, it's really interesting.
What else can we say about this one? I guess the Cat's Eye Nebula is a little more blue than other nebulas, and I guess that's indicative of what the original star was made of. I guess. Does that mean there's more oxygen, Abby?
Yeah, I believe so. I remember more blue means more oxygen present in it.
Oh, okay. And that's where that blue comes from. Yeah, opposed to red, which was, like you said, the hydrogen and helium.
And if you see green or yellowish, it means it's a different kind of elements on the periodic table.
Yeah. So you have the whole range of colors on the periodic table.
Oh, the Ring Nebula. I love it. Every summer we look into the Ring Nebula. It was so pretty.
Oh,
it's like a rainbow.
Such a good one. And that was in the summer, right?
Yeah, that's in the summer.
Dang.
It'll be a while before we can look into that.
Yeah,
maybe exactly. in next few months.
Oh, exactly. Let's see here. Just looking in the chat, just seeing how things are going. On the horizon, yeah. Jupiter's setting. Yeah, I think Jupiter is, set already. Or well,
Jupiter, it's already set because it was really low here earlier to begin with.
Yeah, if it isn't set, then it's behind the SFU AQ.
Yeah.
Ooh, which kind of sucks. Are there any other planets that we can see? Because I know Saturn was close to Jupiter, but now that's long gone.
Yeah, I checked earlier today. All of the planets are currently below the horizon, so unfortunately we won't be able to look at planets today.
Okay. Fair enough. Okay.
Yeah.
Let's see.
Yeah. Also, you can see another thing. Okay.
Ooh,
yeah.
You want to try a galaxy?
Ooh, I like galaxies.
We're so ambitious, aren't we? Okay.
We are.
Okay, let's try the cigar galaxy.
Okay, I can do it.
Yeah, go for it.
Okay. Yep, cigar galaxy. Yeah, totally. Yeah, good spot. Yeah, we can look at it.
Okay, let's try. All right, so the cigar galaxy, just as we're in transition, or another name is M82 by its Messier catalog, is a galaxy that we're seeing edge on. So we don't see any spiral, any kind of spiral or any kind of other features that would tell us it's a galaxy. And I'm just trying to see what the distance is. Yes, 12 million light years from Earth. So now we're in the millions in terms of light years. And I was gonna say, and if you look at a really good photo of it on online, there's lots of like dust and gas. Oh, geez, look at that. Oh, that looks so cool.
Yeah. It's all a bit, on the lower edge of the,
Lower
of the
edge.
frame. But yeah, we can still see it.
Here, let's see. I'm gonna try one thing really quick, and maybe I can
Okay, yeah.
see what
Take
we
over.
can try here. So that's down there. What if we go here? Just gonna clear it. Here again. That looks like it went to the side. That didn't really help. So I was saying, yeah, so there's lots of dust and gas that's in the galaxy, so that means there's lots of star formation.
Yeah, you're right. It's actually classified as a starburst galaxy, and starburst galaxy actually refers to galaxies that has unusual high rates of star formation. So, yeah, there are a lot of star formation activity in this galaxy.
Unusually high. Oh, interesting. Unusually high. So typically that means that maybe a big object came through the galaxy and might have disrupted the, maybe not the shape, but disrupted the galaxy in order to spark more star formation. See, my mouth is faster than my brain, so I gotta talk slower. So maybe that's what happened, because there's some galaxies that have smaller ones orbiting them, just like the Milky Way does. The large and small Magellanic Clouds are actually dwarf galaxies that are orbiting our own. It's just unfortunately we can't really see them in the northern hemisphere. You can only see them in the southern. But maybe something like that happened, where another galaxy just slammed into this one and ignites star formation. But this is an entirely different galaxy, which just looking at it is just like, oh my god.
Yeah, it's so cool to look at different types of galaxies. Because when I was younger, I just imagined galaxy like most of the pictures you saw on the internet, just like a swirl looking like one of those hurricane. But turns out there are different shapes of galaxies, and they're really nice. They look super cool.
Yeah. Wow. And it also, just looking at it, it looks like there's like a piece missing through the center. Like almost looks like it's cut in half. And that's actually due to one of the like it's just a little bit thicker in terms of gas that's just going past that part of the galaxy. So it looks like it's cut in half. Oh.
Oh, so beautiful.
So cool. Alright. Just checking the chat. See how we're doing. Things are going good. What else can we say?
Let's see.
12 million light years from Earth. That's incredibly far away. Yeah. And the thing is, like, I'm just thinking about in terms of the shapes of galaxies too. Like the whole, some have spiral shapes, so they're called spiral galaxies. There's some that are called barred spiral galaxies. So that's where a galaxy has a central, almost like a bar that's going right across the center, and then spiral arms come off of the edges of the bar. That's called a barred spiral, and I think our own Milky Way is a barred spiral galaxy.
Yeah, it is. Our own Milky Way is an example of barred spiral, and you mentioned spiral galaxies earlier, and apparently our neighboring galaxy, the Andromeda galaxy, it's a spiral galaxy. If you look into the image, I mean, you couldn't see a very specific bar coming out from the bulge in the center of the galaxy, but you can still see the swirl. So that's why it's called a spiral galaxy.
Okay, yeah. Okay. And even how these galaxies take shape is still an active area of astronomy research right now. Still don't entirely know why they get their shapes.
Yeah, maybe it's some people from the audience, they might know in the future if they're into astronomy research.
Mm-hmm. Yeah. Study galaxy formation is really, really cool. Let's see here. So that was Cigar.
Yeah,
What's
maybe
another
we could look at its neighbor, M81 the Bolt's galaxy. It's pretty close.
Sure, let's give it a try.
Yep.
Let's do it.
Okay, let's give it a swirl. Let's try. Let's try that. I hope it will look nice. Oh, yep. Yeah, I can see the bulge.
And this was M82?
The last one was M82. We're now looking at M81.
Oh, M81. Got it. Okay.
Yeah. Cal, do you want to move it around just like you did for the last one?
Oh yeah, sure. So how far away is this beast? This. Let's have a look. Oh, this one's actually a little bit closer at 11.6 million light years from Earth, where the Cigar was 12. You know, it's only 400,000 light years closer. Just talking these distances is incredible.
It's so hard to imagine that. I mean, because it's some places that you would not be able to visit in your lifetime, or maybe in your next few generations. So yeah, it's just crazy to think about the distance, even though if it's within the Milky Way.
All right. Oh, okay. So yeah, there it is at the top there. If we just let the images come in and stack, I think in a few minutes it should we should be able to see some structure.
Yeah.
What I mean is like seeing the arms.
Yeah, I can see a little bit now. You can see there's a bulb. Yeah, I can see the center of the galaxy, and you can see like a bulb, a really fuzzy patch around it. So I believe those are the arms of the galaxy.
Oh, cool. Okay.
Yeah.
Awesome. This is again a whole another galaxy. Oh. And actually, a really neat way to tell how old a galaxy is looking at the kind of the color of most of the stars that are in that galaxy. And what I mean is kind of like what we were discussing where star clusters like the Pleiades, it's younger in addition to being, more farther apart and sparse. The stars themselves are, more blue. So they burn hotter and they don't live as long. You can apply the same logic to galaxies. Oh, excuse me. Apply the same logic to galaxies, and I'm just seeing now. Xena has got it in the chat there as well. But the more orange or red the stars are in the galaxies, of course there'll be some blue ones, but if you have more orange and more red stars, it's kind of indicating that it's an older galaxy. Because red dwarf stars and yellow stars, they live longer than blue stars. Really, really cool.
It is.
Still, some of the structure still isn't really coming out very well. But I can see what you mean, where it's like there's a.
Oops. Okay, I'm trying to move the mid level.
Go for it.
Yep. Yeah, you can see a little fuzzy yellow, but a little bit blow up in here. So I think that's the galaxy, but the core is super bright.
Wow.
Yeah, and actually M81, it's also called the Bode galaxy, and it's also one of the galaxy that's relatively closer to us. So yeah, it's always been studied by astronomers. Just an interesting fun fact.
Huh. Interesting. Okay. Let's see. Okay, so just starting to wind down at least. We got about another 15, 20 minutes or so. What would be a good final object to look at?
Let's look at it. I think. Let's see if any clusters are available. Because we haven't looked at clusters tonight.
Yes. Is M3 good?
M3, let's see, because earlier I checked, M3 is still a little bit low. But yeah, we can try that again. Oh, sadly, it's still below the horizon. Yeah, actually we can search it here because globular clusters are usually indicated a yellow ball with a cross on it.
Be tricky to pick out. Oh yeah, so there you go.
Yeah.
Really interesting, actually, while we're looking for a star cluster, is a lot of the star clusters that we see, like if you look at a star chart or star chart or any kind of picture of the galaxy, a lot of star clusters, the symbol for a star cluster is usually a circle with a cross in it. Most of them that you'll see lie along the Milky Way itself. Now, what that kind of indicates is that most of the star clusters are surrounding the nucleus of our galaxy, also called the galactic halo. But most of the star clusters are surrounding the center of the galaxy, and that is also an area of active research in the astronomy community, is why that is. Because it's also part of galaxy formation is that most of these star clusters are around the center or galaxy. We don't quite know why that is. What do you got?
So I got this. It's called like NGC 188, and actually you're right about circle indicating clusters. So there are differences. So you can see, for example, try to drag this here. You can see some of them are just yellow circle with the edge. Those are open clusters, and usually globular clusters are the one with the cross on it.
Here, let me drag it a little bit further. Oops.
Yeah, no worries.
Where'd it go? Oh, right there.
Okay. Where did?
No, I got it. I got it.
Okay. Yeah,
Right,
you got it.
Right there. Okay. And
yeah. So when you guys are exploring those one of those stargazing software like Stellarium, this is how you can tell it is. Yeah, you can tell objects apart. So usually for open clusters, they're indicated in a yellow circle without a cross in it. For a globular cluster, they're indicated with a colored yellow with the cross on it. And the green dots, those green dots where you can see there's two colors, those are planetary nebula. So sometimes instead of going to Google and search list of planetary nebula, this is also another faster way where we could find objects, just like what we're doing now. We're running out of some of the objects that we can see. This is how we can find some objects quick.
Come back. Oh no.
Okay.
See,
we can close.
We try and show something nice and informative, and just kind of scrambles. Okay. Where'd you go? Okay, so we're gonna drag you over. We're gonna get
dragging back because we're pointing at something, and
let's drag this back just a little more. Really? And then it just goes away. I'm back. Don't be shy. How come it says as soon as I get there, it just goes away? Boom. Boom.
hey,
That'll do. That'll do for now.
Yeah.
Let me just minimize this. Okay. Let me bring that right there. Perfect.
Mm-hmm.
All right. Let's do it.
Yep. So let's see.
Okay. So it's a little hazy. That might be due to the clouds, unfortunately.
Mm-hmm. Yes, it is. Yeah, I guess the clouds are rolling in, so it's a little bit harder to look at objects.
And it's kind of unfortunate. A lot of the cool stuff. I mean, all star clusters are cool. I'll say that. But some of the really popular ones, I'll say, are unfortunately below the horizon right now, which kind of sucks.
Mhm. Let me see if we're pointing at the right location. It's a little. Yep, we should be pointing at the right place.
So I guess is this a little more diffuse star cluster? It looks like.
Okay. Okay, there is another object where we could try.
Okay. Oh, this should be good.
Yeah, this is a nice one. And we just mentioned it earlier.
Oh, it might be too big for the aperture, but we'll see.
It might be a little bit too big for the aperture. Yep, let's see.
Waiting, stack the images.
And let's see that.
So we'll have to balance the colors. Kaleidoscope of colors.
Okay, I can see a really tiny bulb under here, but I think it's a cloud because we're not picking up a lot of background stars for aligning the objects.
Yes. What we're looking at, or trying to at least, is the Andromeda galaxy. Just like, what object that Abby mentioned a little while ago. And this is the closest galaxy to, I'll say closest, like, full-on galaxy to our own. It's our neighbor. Hello, neighbor. What can you tell us about it?
So yeah, the Andromeda is the closest galaxy to us, like Cal mentioned. And do you know that our galaxy and Andromeda galaxy is actually colliding with each other in the future? So yeah, both of us are going towards each other.
So Andromeda is coming towards us. Right? Oh.
Yeah. It might sound very scary, but actually it's not like a car crash you would imagine, since there are a lot of space in between stars in a galaxy actually. So it will be more likely, it will be like throwing two piles of sand towards each other instead of, a really horrible car crash that you would imagine. So yeah, but that's also happening in the far future. I forgot how many years exactly. I'm sorry about that, but yeah, it's happening in the far future.
I think a few billion or something like that.
Mm-hmm.
So, excuse me, yeah, so, and the clever name that astronomers have come up with the combined galaxy is something, okay, I think it was Milkomedia. I think that was the name of it, which is, yeah, that's all right.
Yeah, I think that's the name. You're just combining names together.
Yeah.
That's so funny.
I'll say this, though. I think...
I also heard one of them that says, like, called Milkdromeda. That's also another version I've heard of.
Or Milkdromeda, yeah. Some kind of combination. One interesting thing, though, is I think our sun will die before we hit Andromeda. It's kind of that far away.
Mhm.
So, yeah, I'm just looking at the chat, and I see that, yeah, some concerns, about the human race. But I think we'll be, if we haven't colonized the entire galaxy by then, I think we'll be fine. And
Yeah.
yeah, it's just like there's so much space, stars will just kind of whiz by us. There won't be any collisions, kind of like what you just said. It's just actually, there's a really cool animation of this online. Okay, let's see if I can quickly find it here. Yeah, Milky Way collision simulation. I think this is really, really neat. Okay, this one I found just on YouTube. Or you can just go to YouTube too. I mean, that's fine as well. But
Yeah.
all right, so let me just go. Let's do this. Okay, so just kind of put the link in just a YouTube video in the chat there, and just look at the time that's kind of that's just increasing. Like we're fast forwarding in billions of years, right? Like it is crazy how this happens. Everything's just so far away. Wow. Anyway, but and there will be one big happy family of a galaxy.
Yeah.
See. I think that's yeah.
That's pretty much it. Yeah. I think we could do there's another cluster should be nearby.
Should be pretty good. Sure.
Yeah, there's another this is an open cluster that we can look at. Yeah, I've been fixated myself towards globular clusters, but yeah, I think it's not the season for globular clusters.
Yeah, I guess not. But this will be the last object because I think we're pretty close to the end here.
Yeah.
So this kind of be our last object, and then we'll see where we go. See where we go from here. So what's the name of this cluster?
So this is M35. There are a couple of really, really nice open clusters in the constellation Gemini.
Okay.
Yeah.
M35, you said.
Yes, it is. Oh, so, yeah.
Ooh, that looks cool. Whoa. So yeah, kind of like we said, so we got an open cluster here, and it looks like there's lots of blue stars. Again.
And a couple of red stars, too.
Oh, and a few red. Okay. So it's kind of getting there in terms of maybe not quite a teenager anymore. But it's got some big ones. So this one's about 3,870 light years away. Pretty much 4,000 light years away. And this is a little older. This is almost 200 million years old. And yeah, evidence with exactly like those red stars there. And in terms of the diameter of the entire cluster itself, it's about 11 light years across. So it's pretty big.
Yeah, I should have gone with bin 1, which can give a more crisp picture, not like a less pixelated.
Oh, we can.
Yeah, well, we'll try it next time.
Or next time. Yeah, that works too. I think we're a little bit over time anyway. But yeah. So I think kind of what can I say? So that's our little tour of a quick tour of the local objects in the universe. I just want to thank you all for joining us, and again, I want to thank Rohit, Zena, and Rob for helping us out in the chat. Again, because of the state of the pandemic right now, we had to move to online again. Hopefully, we can go back to in person soon. I remember we had one last year, and that was really cool. But
yep, I'm looking forward for that too.
Hopefully, we can go back and see everyone's wonderful faces. That's what's important, is to share the night sky with our friends and family. Right.
All right.
Any closing things for you, Abby?
Yeah, thanks everyone for joining us tonight. Yeah, and thank you for being so patient. Even though we're a little bit late, we're running behind occasionally. Yeah, but thank you for being so patient with us. Yeah, and thanks for joining us tonight.
Awesome. Thank you all. Have a good night. Keep looking up.